So previous video, we just went through what it means for capacitors to be connected in series, the equations that are specific to capacitors connected in series, and that capacitors in series have the same charge. The second way to connect capacitors is called parallel. So I'm again going to draw my battery as a long line and a short line. Long line always means the positive terminal. Short line means the negative terminal of the battery. I'm going to go ahead and use the EMF symbol to represent our ideal battery. In parallel, we take a wire, we connect it to one side of our capacitor, and then the other side of the capacitor, we take a wire and go back to the battery. Our second capacitor, somewhere in this wiring, we could even put it on the terminal of the battery itself. We take a wire that separately, independently, goes to a different capacitor, C2, and that wire goes back to the battery. Technically, the battery itself, we could have two different wires, one that comes off to C1 and one that goes off to C2. It wouldn't be very pretty, but it works just fine. We tend to draw this a little prettier than what I just scribbled below. We can continue adding capacitors like this, but in each case, going back to following a path. Let me erase my mess right here because that's a little annoying. If I start at the positive terminal of this battery and start following the path, I get to a point right here called a junction. At this point, I have two choices. I can totally choose to come down past C1 and get back to the battery. That means there is a path possible where I only have to pass C1. I don't have to pass C2 or C3. Similarly, I could be coming from the battery, get to this junction, but choose to go straight and come to another junction. Here, I choose either to go down and pass C2, which in turn will take me back to the battery, or I could have gone straight and passed C3 and then gone back to the battery. Whenever we have junctions where there is a choice to be made, we can only follow one path at a time. If you think about going hiking, you go hiking and there's perhaps a couple ways to get to that beautiful waterfall at the end. You personally can only walk one path at one time. You might go back on another day and walk a different path. That's totally fine. But at one specific moment in time, you can only take one path. And that's what we're looking at here. For any one path we choose to draw in the circuit, we have to make a choice at the junction. So in this case, because in our three possible paths, we can choose to go through C1 or through C2 or through C3. That's what makes them be connected in parallel. So parallel means there's some sort of junction, so there's a choice in the path we are drawing or following through our circuit. Now let me draw this again to talk about electric potential. I'm just redrawing the same picture. So getting my wires all drawn in here, my battery, long end is positive, short end is negative. If we think about the equilibrium situation again, where we said that everything that is conductively connected like the positive terminal of the battery, and all wires and the wires connected to, since we're talking about the equilibrium situation, all of this that is conductively connected, sorry, that was supposed to be a plus, has the same potential. So in this case of having a parallel connection, the top plate of each of these three capacitors ends up at the same positive potential. If we think about the negative plate, negative plate, the wires connected to it, the capacitor plates connected to those wires, all of this will end up at the same negative potential, which means these bottom plates all have the same negative potential as the battery, its negative potential. If we look at each of these plates individually, that means each of these capacitors initially, so like capacitor 1, if we say capacitor 1 has potential difference of delta V1, and capacitor 2 has potential difference delta V2, and capacitor 3 has potential difference delta V3, these are all equal. In this particular case, they're equal to that battery voltage. In parallel, they have to have the same potential difference. And that's just the nature of how this equilibrium is reached and what we mean by electrostatic equilibrium. Everything conductively connected ends up at the same electric potential. And so we end up with our capacitors having the same delta V. If we think about our equation relating charge and delta V, if they have the same delta V but different C's, then they're going to have different amounts of charge. So for example, just find a different color. The charge on C1, we could call that Q1. That would represent however much charge accumulated on the plates. That would equal C1 times delta V1. For capacitor 2, the charge that accumulates on either plate would be C2 times delta V2. Similarly, for the third capacitor, we would end up with a Q3, C3 and delta V3. Q1, Q2, and Q3 are not the same if C1, C2, and C3 are not the same. So let's think about charge for a second. We're using the traditional definition of protons moving. If I imagine some charges, I'm going to just use E to represent this. Some number of charges, so capital N, the number of charges, E is the charge on them. They start moving through the circuit. But they reach a junction. Charges are actual physical objects with mass. They can only take one path at a time. Some of those charges, Q1 amount of charges, will come down to capacitor 1, but some of them will continue. At this next junction, some charges come down to charge capacitor 2, but some of them continue to charge capacitor 3. Similarly, if we think about charges flowing back, this Q3 would combine back together with Q2 to head back this way, which would then combine back together with Q1 back this way. I'm going to say some total amount of charge that needs to move to get this circuit to equilibrium. Total amount of charge needed to get the circuit into equilibrium. And by that, I mean the total amount of charge needed to get all three of these capacitors at the same potential difference. That charge, because it keeps splitting off at these junctions, mathematically we can say some of it goes to capacitor 1, some of it goes to capacitor 2, and some of it goes to capacitor 3. But when we add those charges up, they must add up to represent this total amount of charge that had to move to get to equilibrium. So this is unique to capacitors in parallel. Similar to what we did with series, not exactly the same, just similar, we can say, using this equation up here, that Q1 would be C1 times delta V1, meaning the capacitance of capacitor 1 times the potential difference that capacitor 1 ends up with across it. Well, Q2 would be a C2 delta V2. Q3 would be a C3 delta V3. The total we could represent, not as Q, sorry, as a C equivalent times a battery voltage. Meaning this circuit with three capacitors in parallel would be equal to, or the same as, this bottom line doesn't want to erase, having one capacitor with a value that we're calling equivalent capacitance so theoretically we could just put one capacitor in this circuit and it would end up storing just as much energy as these three connected together in parallel. That's what we mean by equivalent capacitance. But when we're talking equivalent capacitance, we're getting back down to this single capacitor. And remember, the charge on a single capacitor is its capacitance times the battery voltage in this equilibrium state. So that's what I'm putting in for Q total here. Q total represents whatever amount of charge is moving to get the circuit in equilibrium. It's the same total amount of charge that has to move around regardless of whether we have the three in parallel or whatever capacitance is equivalent to that. Well, in parallel though, these all have the same delta V's. So this tells me that the value of this one capacitor that would be the same as having the three in parallel is simply the sum of those three capacitor values. So we get a bigger overall capacitance. Which means we could then in turn find out how much charge was on each capacitor. So for example, let me just make up some numbers here. Battery again, I guess. Let's say C1 is 5 microfarads. C2, I don't know, 15 microfarads. Oops, forgot my capacitor. C3, let's go with the 5s this time. So we'll go to 25 microfarads. If I wanted the potential difference and charge, like I did with the series example, find the charge and potential difference for each capacitor. Well, the nice thing is, I know these are all in parallel. And by the way, be careful when you look at a picture. I highly recommend always just tracing a path to see if you have a choice or not. Don't assume what the connection is. Follow a path around your circuit. In this case, this is the same setup as we just looked at. So we already know these are all in parallel, which means not only do they have the same potential difference, they have the same potential difference as the battery. So capacitor 1 has a delta V1. That is its potential difference. Capacitor 2, delta V2. Capacitor 3, delta V3. These are all going to be 12 volts in this situation because they're all connected to this same battery. The charge on each one, we don't actually need to get down to an equivalent in this particular case to answer this question, because we find charge from our equation Q equals C delta V for the capacitor. We already know their capacitances because that's in the picture. We know they're in parallel and in parallel with this battery, so we know that they all have 12 volts across them. So Q1, meaning the charge on capacitor 1, will be its capacitance times the potential difference across it. So 5 microfarads times 12 volts. So Q1 is 60 micro. The farad times the volt is what gives us the coulombs. So that is the charge on that first capacitor that I called C1. C2, well, the charge on that will be its capacitance times its potential difference. So its capacitance is 15. Its potential difference is 12 volts. I did not choose numbers that would be easy to multiply because I didn't think about it. 180 microcoulombs is what that ends up being. The third capacitor, its charge Q3, same equation, but using values for that capacitor specifically. So its capacitance is 25 microfarads. It too has 12 volts across it. 300 microcoulombs. So they have different amounts of charge because they have different capacitances. I do want to show you one other thing though. Let's go ahead and draw this and calculate an equivalent capacitance. These are in parallel, are equivalent. Well, we saw C equivalent for capacitors in parallel simply adding them together. So 5 microfarads plus 15 plus 25, 30, 45 microfarads. The charge on this equivalent capacitor. Because we're now at a situation where we have one single capacitor, we know that one single capacitor's potential difference will be the battery voltage. 45 microfarads times 12 volts. Is 540. Q1 plus Q2 plus Q3 is 540. This is a conservation of charge representation. Whatever charges start moving, so when we talk about some sort of Q total that has to move in order for this circuit to come to equilibrium, they have to keep flowing. Some of them come to here, Q1, some of them continue where some come to here, Q2, some of them continue to come to here, Q3. We cannot lose or gain charges from what we had to move in order to reach equilibrium. So in parallel, it turns out that however many branches the charges can follow, if we add those charges up for those branches individually, they will add up to equal the charge on their equivalent. Okay, the hard part of this is conceptualizing it all. The equations are not hard to use. We have used this equation many times. The last 2 videos, we used it over and over and over again. So the equation itself is not hard. It was not hard to plug values in to find C equivalent here or for the series. So the equations themselves are not particularly difficult, but we have to be able to reason through whether we have series connections or parallel, or we might have a combination of series and parallel. And so from that, we have to reason what capacitors in series have the same, what capacitors in parallel have the same, in order to solve our problems. So we'll look at some examples where we have a combination of series and parallel and how to approach problems in that regard, as well as do a few examples.